Sections 4.2 and 4.4 deal with optimization, geometry, and modeling. And the goal of these sections is to use the technique of finding and classifying critical points, which is what we did in section 4.1, in order to maximize or minimize a prescribed quantity in a given context. So to address these types of problems, we're going to need to use some formulas from geometry, just to summarize those which we might use. There's the formula for the area of a circle of radius r, pi r squared. The circumference of a circle of radius r, 2 pi r. The volume of a box having dimensions L by W by H, length, width, and height is LWH. And then the volume of a cylinder of radius r and height h, which is pi r squared h. I always just remember this. It's the area of the circle times the height of the cylinder. So we're going to take a look at a couple examples in this video. The first one is as follows. A box with an open top is to be constructed from a rectangular metal sheet of dimensions 60 by 40 centimeters. By cutting out a square from each corner, what are the dimensions of the box that yield the maximum volume? Now the solution process we're going to use, which is quite similar for all types of problems, is as follows. We of course draw a picture and label various dimensions using letters that make sense. L for length, W for width, R for radius, and so on and so forth. Then we determine a formula in terms of the labeled quantities for what we wish to maximize. So in the case above, we want to maximize the volume. So we're going to find a formula for the volume in terms of what we've labeled in part 1. If the formula from this part contains more than one variable, then we use other provided information and necessary substitutions to rewrite it in terms of a single variable. That's important, a single variable. And then we write down the interval of permissible values for the variable that makes sense for the problem situation. And then lastly, we determine the global or absolute maximum of the formula from 3 by performing the critical point analysis, the type of which we've done in section 4.1 on the recent activity. So let's take a look at that particular example. We have we have a sheet of dimensions 60 centimeters by 40 centimeters. So I'm going to label this as 40 and this is 60, and we want to cut a little square out of each corner and then fold things up so that we have a picture that looks like following. So because we're cutting a square out of each side, we don't know its dimension. I'm just going to label the dimension of the square to be x. So that means that this is x, this is x, this is x, this is x, and so on and so forth. These are all squares, length x on each side. So I take my box and I fold it up so that what's left here, I'll call it A, shows up down here. What's left here, which I'll call B, shows up right here. And then from the way I fold this thing up, the height of the box is going to be x. So the volume is going to be the height times A times B. We could call A the length and B the width, or vice versa. It doesn't really matter. Now whatever we decide to call this, be it length or width, we can see that A is going to be the entire 60 centimeters. And then we're going to subtract this x and then this x again, so that this dimension is merely that dimension. So A is 60 minus x minus another x, which is 60 minus 2x. Now B represents this distance, which is the same as that distance. And B will be 40 minus x, again this is x, minus another x, which is 40 minus 2x. So let's see if we can write down the volume of the box. The volume will be the height times this dimension A, which is 60 minus 2x, times this dimension B, which is 40 minus 2x. And this can be expanded. I've performed it separately, the calculation. It works out to be 4x to the third minus 200x squared plus 2400x. Now, in this example, we got the volume, which we're trying to maximize, immediately down to a single variable, one variable, which is x. We're going to do another example in a moment where it's not quite as simple. Now, we also need to determine the interval of permissible values for the particular problem. X has to be greater than or equal to 0 because it's a dimension. In fact, it has to be greater than 0 because if X were 0, the volume of the box would be 0 to start with. On the other hand, we also need to realize that we can't cut too much out here. If X and X together added is greater than 60, or if X and X adds up to be equal or greater than or equal to 40, there's really nothing left. So we can rephrase that by saying that the quantity 60 minus 2x, which is just a, has to be greater than or equal to 0, and the quantity 40 minus 2x has to be greater than or equal to 0. Again, that's because we're limited by how much we can cut out. If we solve this for x, it says that 30 has to be greater than or equal to x. If we do the same thing here, this says that x has to be less than or equal to 20. So the more restrictive of those two is that x has to be less than or equal to 20. So that says that the permissible values of x have to lie between 0 and 20, and actually not including 0, not including 20, because then the volume would be 0. So we want now to maximize the volume, restricting our x values to be between 0 and 20. So if we want to maximize something, we first compute, there's our volume, we first compute the derivative and we set it equal to 0. This is exactly the process we used for finding local extrema, local maxima, and local minima in section 4.1. So here's the derivative. It's a quadratic. I use the quadratic formula, minus b plus or minus b squared minus 4ac all over 2a. This is 400 plus or minus the square root of 44,800 all over 24. This can be simplified. I'll let you verify that on your own. It's 50 thirds plus or minus 80 times the square root of 7 over 24, which simplifies to be 50 thirds plus or minus 10 times the square root of 7 over 3. Now these are the exact values, but for subsequent calculations, we'll just go ahead and use their decimal approximations. If we use the plus value, we get 25.4858. Now we have to throw that out because, of course, x has to be less than 20. We discussed that a moment ago. So that means the only critical value is 7.8475. We don't know whether that corresponds to a maxima or minima, so we have to do something else. Perhaps use the first derivative test, or in this case, I'm going to use the second derivative test. The first derivative was 12x squared minus 400x plus 2400. So the second derivative would be 24x minus 400. If I plug my 7.8475 critical value into that, I get something which is negative. That tells me then by the second derivative that 50 over 3 minus 10 root 7 over 3, which is about 7.845 centimeters, is a local maximum. In fact, if we go back and check the endpoints of our interval, if we plug either 0 or 20 into the volume formula, we get a box of 0 volume. So that means that 7.8475, this value, is the global minimum. Now, we need to also find the corresponding volume and the other dimensions. The volume is obtained by plugging our x value of 7.8475 into the volume formula. That works out to be about 8,450 cubic centimeters. We also need to find the other dimensions. The length is 60 minus 2x, which works out to be 44.305. The width is 40 minus 2x, which is about 24.305 centimeters. And so those give us the remaining dimensions of the box. So our final answer is that we cut out about 7.8475 from each corner. That yields a box of about 8,450 cubic centimeters, and then these are the dimensions of the length and the width, respectively. Let's go on to a slightly harder example where we really, in fact, have to make the substitution. Okay, a can of soda has a volume of 355 milliliters. A milliliter is a cubic centimeters. What dimensions will yield the can if possible, smallest possible surface area? So here's a picture. We have a can of soda. We know the volume has to be 355 cubic centimeters. And we're trying to minimize the surface area. Now the surface area would be how much paint you need to paint the entire outside of the can. So in other words, it's going to be the area of the top plus the area of the bottom of the can plus the area of the side as we go around. So let's do what we did, similar in the last example. Let's label some dimensions here. Let's label the radius r. Let's label the height h. Now the quantity we're trying to minimize in this case is not a volume. We're not trying to maximize a volume. We are trying to minimize an area, the surface area. So we're going to write down a formula for the area of this can, the surface area. Now the top is pi r squared, and so is the bottom. So the area of the top and the bottom together would be 2 pi r squared. Now we have to find the area of the side, and this is a little bit tricky. Here's where we're going to have to use h. Imagine, if you will, forgetting about the top and the bottom, and just taking the side of the can and cutting it down this way and laying it down flat. And if you did that, you would get something that looks like this. The height of this rectangle, the rectangle is what we get by laying the sides down flat, the height would be h, and the length would be the length around the top of the can. That would be the circumference, 2 pi r. So that means that the total area is equal to 2 pi r squared plus 2 pi r times h. R is the radius and h is the height of our can. Again, it's r and h that we're trying to figure out. Now, in the previous example, once we got to the volume, which was what we were trying to maximize, we had just one variable. So we were all set. We could compute the derivative, set it to 0, and find the critical points. In this example, a little more work is involved. Here's where we have to go back and use number 3. If the formula that we have contains more than one variable, use other provided information and necessary substitutions to rewrite it in terms of a single variable. So we have two variables here, r and h. We need to get rid of one of them and get a formula just in terms of r and h. And this involves a substitution. Here's where we use the fact that the volume is 355 cubic centimeters, and the volume of the cylinder would be pi times r squared times h. Now we have a couple options. We can solve this for r and then substitute the result in for h up here. Or we can solve this for h and substitute it in for, let me say that again. Solve this for h and substitute in right there, so we get this in terms of r, or solve in terms of r, so we have r in terms of h, and everywhere we see an r, we substitute that formula. Now, it really doesn't matter in terms of the final answer which is correct. You can go either way, but one is going to be computationally easier. If we solve for r in this formula, pi r squared h equals 355, we divide by pi h and we get r squared, and then r would be the square root of 355 over pi h. Now the difficulty with this, we could do this, is that if we substitute that in right here, we're going to eventually have to take the square root. We're going to have to take this quantity and compute its derivative, and that could get a little bit messier. On the other hand, if we simply take this and solve it for h, we can substitute this in right there, and we'll have a little bit of cancellation. There won't be any square roots involved, and the derivative process will be a tad easier. So let's do that. We're going to take 355 divided by pi r squared, that's h, and we're going to substitute it in right here. So we have 2 pi r squared plus 2 pi r, and then I substituted 355 over pi r squared in for h there. We have then 2 pi r squared plus, we can simplify this, 2 times 355 is 710. The pi's cancel. R over r squared is r. Now we have a formula for the area in terms of one variable, that one variable being the radius. Let's figure out what radius will minimize the surface area. So we've completed steps 1 through 3, and we should note that r has to be strictly greater than 0. It can be as large as it wants to be, but intuitively, the larger the r, the smaller the h. So let's compute the derivative. First, we simplified and we got 710 over r, and we're going to be computing the derivative, so let's just remind ourselves that 710 over r is 710 times r to the negative 1. So a prime would be, by the power rule, 4 pi r, and the derivative of this, bring the minus down in front, minus 710 times r to the negative 2. We set this to 0, and we solve for r. Now here we're not going to use the quadratic formula, we're actually going to just manipulate things algebraically. We'll get the 710 over r squared on the left side. That's equal to 4 pi r. Then we cross multiply and divide by 4 pi. So 710 divided by 4 pi is equal to r to the third. If we take the cube root of that, r is the cube root of 710 over 4 pi, which is about 3.84. Now we need to assess whether this corresponds to a maximum or minimum. If we compute the second derivative, we get 4 pi minus, bring that minus 2 down in front, so that minus 2 becomes a plus 2 times 710 times r to the negative third. And if I plug my 3.84 into this, I get something which is positive. I don't even really need to evaluate it here. Once I look at this, I see that I have something that's positive. And I think this is correct. I may have forgotten to raise this to the minus 3 power. But in any event, I can actually see that so long as r is positive, a double prime is going to be positive. So this will be a local minimum by the second derivative test. Now we go back and we determine the corresponding values of h and r. Remember, r cannot be 0 because then we'd have a can of volume. H was 355 over pi r squared. If we plug in our r value 3.84, we get about 7.67. We also want to take that h value and that r value, plug it back into the surface area formula. This tells me that the surface area is about 277.545 square centimeters. So to summarize, r is about 3.84 centimeters, h is about 7.67 centimeters, and the volume is about this. And it's interesting to observe that if this was indeed under this scenario, this says that this radius is about 3.84, which is about half the height. So in other words, as you look at the can, it would actually have a square profile. And of course, this is not the case in real life, and the primary reason is that the tops and the bottoms of the cans actually cost more. So we take that into account by making the area of the top and the bottom smaller.